Welcome back. The vascular system. So if you recall what we talked about in regard to the cardiovascular system, we talk about the three components of the cardiovascular system would be blood, blood vessels, and the heart. The vascular system basically it refers to the blood vessels. So the vascular system of the blood vessels, or we can say it refers to blood vessels. So first question is what is the function of the vascular system? And the main function is transports blood throughout the body through the use of blood vessels. So when you ask the questions is what exactly are blood vessels? So blood vessels are tubings. So these tubes that run throughout the whole body that help to carry or transport blood throughout the whole body to deliver nutrients to the tissues and drain the waste away from the tissues. So that takes us to the next question is that how many types of blood vessels are there? And we can simply say there are three types of blood vessels. So there are three types of blood vessels. The first type of blood vessel is arteries. And so there are three types of blood vessels, three types of blood vessels, and they are known as arteries, capillaries, and veins. So the arteries. So typically we don't use what we just refer to as, so the three types of blood vessels and the arteries, when you clump them together, they are known as arterial system. The capillaries don't exist individually, they exist as a group of capillaries and it's known as capillary bed. So capillary beds are composed of many capillaries. So as you can see from the image that I have on the right side, this right here is one capillary bed. So you have many capillaries involved or combined together. Okay. So now the third type of blood vessel would be veins, and veins combined together form what is known as the venous system. So once again, is that we ask the question is that what is the function of the arterial system and what is the function of the venous system and what is the function of the capillary beds? Okay, so let's begin on the arterial system. Its main function is, function-wise, we can say the arterial system carries blood away from the heart. This is a very, 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 uh, very conventional. It says this is a conventional definition. It says that the arterial system, by definition, carries blood away from the heart. There's no exception to that. It just carries blood away from the heart. The venous system, on the other hand, function-wise, returns blood back into the heart. So this is a very, very, very standard definition. So you don't need to basically say deoxy or oxy blood. We can say in general, the arterial system carries blood away from the heart. The venous system returns blood back into the heart. So what that means is this, what is the function of the capillary? The capillary beds represent the site where exchanges of nutrients and waste between the interstitial space or between the interstitial fluid within the space and the bloodstream within the capillary. So the interstitial fluid of the tissue and the bloodstream within the capillary. So you can actually see right here is that within the capillary bed, you can see that there are exchanges occurring between the bloodstream and the tissue and the interstitial fluid of the tissues. So now this is a very good discussion, and we'll come back and talk more about this in a moment. And let's go to the left image that we see here. As you can see, within the bloodstream, you have different components. You have plasma, so the plasma is composed of proteins and water, so mostly proteins and water. And then you have the white blood cells, you have the platelets, and then you have the RBC. You can see the image of the RBC here. And all this make up what's known as the blood. So basically, the blood vessels transport blood to and away from the heart. Now, all these blood vessels form what's known as the circuits. This is a review of the circuits. There are two circuits that we have talked about. The first circuit is going to be known as, so this will be, first circuit is known as pulmonary circuit. Now, pulmonary circuit basically tells you that, so what exactly is the pulmonary circuit? Okay, so pulmonary circuit refers to, when you see the word pulmonary, it means the lungs, okay, or pertain to the lungs. So let's refer to the pulmonary circuit. Let's give a quick glimpse of pulmonary circuit. This should be a recap. So the moment the blood leaves it from the right ventricle, it will go into what's known as the pulmonary circuit, where gas exchange occurs at, and it goes back into the left atrium. And this circuit is rather short. Okay, so it's not very long. It's rather short in this case. So we can say pulmonary circuit is going to be very short, shorter in distance. And if you recall what I said, is that the heart is medial to the lungs, which means the lungs are on the two sides of the heart. So the distance to go from the heart into the lungs is very short. It's really short from the heart into the lungs and back into the heart. Is relatively short in distance. And because it's shorter in distance, the resistance is lower. Okay. Now, if you remember what I said, is that the distance and resistance tend to have so there's a correlation in that sense. So typically, the shorter the distance in terms of blood vessels, the resistance is lower. So we will talk about the resistance, what factors contribute to the resistance in a moment. But for now, I also want to make a note is this, and for that reason, the blood pressure in the circuit is lower. Okay. And when I say lower, what does it mean? Lower compared to what? Well, it compares to what's known as the systemic circuit. And systemic circuit, the moment the blood leaves the left ventricle, it goes into what's known as systemic circuit, and it comes back into the right atrium. So as you can see, in the systemic circuit, you also have what's known as the exchanges, but in this case, the exchange. So let's talk about what happened so it's the same concept in this case is that you have gas exchange in the lungs. Okay? Whereas in the systemic circuit, you have exchange of nutrients, including oxygen, which I would consider to be a part of the nutrients, and waste, which including CO2, as you already know what CO2 stands for, right? Carbon dioxide, between the interstitial fluid and bloodstream in capillaries. So this is very crucial for you to understand what exactly happens, because typically people don't think of exchanges occurring inside the systemic circuits or within the systemic circuits. People usually use the word exchange in the pulmonary circuits, but not in the systemic. So in fact, there are exchanges that occur within the systemic circuits, but exchanges in different forms. And as you already know, as we have talked about in past lecture, is that the systemic circuit is relatively longer in distance with more resistance. With we can use the word higher resistance in that sense. And I'm going to try to bring this up so I can have more space to type in for you guys. So to make this perfect, and we can say including, we can move it up here to make it more space for you guys. And bloodstream, we can move up there. Longer in distance with more resistance, with, oh, why don't we say with higher resistance, and for that reason, the blood pressure is in the systemic circuit is higher. Okay. So when you compare between the pulmonary circuit and systemic circuit, you can see a contrast between the exchanges involved, and you can also see the contrast between the distance and the resistance and the blood pressure within the respective circuit. All right, now I'm going to go into a bit more details on this. Now, what we can say from this, based on the image that we have on the right, bottom right, we can see on the left side you have the artery, on the right side you have the vein, and in between you have what's known as capillaries. If you look at the arrow that is shown on the image right here, that means it shows you that in the artery, it carries, or in the arterial system, it carries blood away from the heart, and in the vein, the venous system, I should say, it carries blood back into the heart. Okay. Now, when you see a contrast in color, okay, so typically in many books, in many images that you see, is that the color for arteries tend to be red and the color for veins tend to be blue, and because of the gas content in the arteries and veins. Now, I'm going to basically postpone or defer to that in a moment, and we will come back to that discussion in a moment for that. But for now, I want you to look at the wall of the artery and the wall of the vein in the image that you are looking at. If you notice, the wall for the arteries tend to be thicker and the wall for the vein can be thinner. Okay? And that explains to you what that means with the pressure wise. The thicker wall means the pressure in the artery tends to be higher, and the thinner wall in the vein which means the pressure tends to be lower in the veins. We will come back to it in a moment for that. But I also want to show you the valves right here. Is this the valve? Veins have valves. Arteries do not have valves. Okay, so once again, veins have valves. Arteries do not have valves. All right. Now let's see what else can we talk about before we move on. Okay, that's it. That's pretty much it. And I will come back and discuss more of this in details for you guys. All right. Any question? Write down your question, and we will talk about it, and we will discuss the questions in the Q&A session. Moving on. Now, I briefly mentioned the two circuits involved, the pulmonary circuits and the systemic circuits. Let's go over the circuits in general. What we have is this, okay? So let's begin. For the pulmonary circuits, let's begin with the first one. Look at A, pulmonary circuits, and look at B, systemic circuits. Okay, look at the top image that we have. For A, pulmonary circuits, and for B, systemic circuits. Okay, so let's begin with A. What is so what does it begin? What does it end? Okay, so the route to take in the pulmonary circuits. Okay, so everything begins in the pulmonary circuit. Everything begins the moment it leaves what's known as the right ventricle. It goes into the pulmonary circuit and it comes back into the left atrium. To be more precise on this, we can actually go into more details. The pulmonary circuit, in fact, to be more precise, the pulmonary circuit, in fact, we can go with right ventricle. And this is going to be what's known as pulmonary circuit, pulmonary trunk. If you recall what I said, the pulmonary trunk is going to bifurcate into what's known as pulmonary arteries, and the pulmonary arteries, there are two of them, and the pulmonary arteries will deliver blood into what's called the pulmonary capillaries, which is where gas exchange occurs at, and which then delivers blood back into the pulmonary veins before it goes back into the left atrium. Okay, so I want you to know, as you can see from what I wrote on the underneath the basic of what I described as the route of pulmonary circuit. Okay. The moment it leaves what's known as the right ventricle, that goes into what's known as the pulmonary circuit. So the beginning of the pulmonary circuit is going to be what's known as pulmonary trunk. So keep in mind, this pulmonary trunk is the first initial site of the pulmonary circuit. So once again, let me just basically just write down here to make it, to reiterate what we have. Pulmonary circuit basically begins right here at what's known as pulmonary trunk, which bifurcates into pulmonary arteries, which then delivers blood into pulmonary capillaries. This is where the gas exchange occurs at. Gas exchange occurs at. And which then goes back into what's called pulmonary veins. So if someone were to ask you, is that where's the initial location of the pulmonary circuit? And the answer would be pulmonary trunk. The next question is that where is the initial site of the ending sites of the pulmonary circuit? And the answer would be pulmonary veins. Now, I also want you to know there's one pulmonary trunk which is bigger in size So you can see right here is that there's one pulmonary trunk right here, and the pulmonary trunk is going to bifurcate into what's known as pulmonary arteries. So the trunk is going to bifurcate. So there are two pulmonary arteries. So the P is for pulmonary, and I'll write out the word pulmonary so you won't be confused on this. Pulmonary. Okay. Now there are two pulmonary arteries, and as you know, the pulmonary arteries will branch out and form pulmonary capillaries. So now pulmonary capillaries. So the reason why there are two of them is because one artery per lung, and there are two lungs. Yes. Okay. Now the next thing is this. There are 4 pulmonary veins. Keep that in mind. So the next question is, what is the gas content for the pulmonary circuit? Okay. So what we can say is this is the oxygenated blood in the first half of the circuit. So when I say the first half of the circuit, that means it's going to be 1 and 2. And the next one is going to be oxygenated blood in the latter half of the circuit, which makes sense. So when you look at the image that we see up here, look at the image on both images, but let's go with A first. And in A, what that means is that in A, what we see in A is that you see the color of the blood vessels of the first half of the pulmonary circuit is blue, which means that the gas in there is deoxy, or the blood is deoxy, and the second half of the circuit is red, which means it's oxy. Okay? Now the length of this is relatively shorter in length, as we discussed this before, shorter in length. Now the resistance, because it's shorter in length, the resistance is lower resistance. Okay, very good. Now the next question is blood pressure. Ooh, that's the next question. So if you recall what I said a while back, I said the blood pressure in the pulmonary circuit tends to be lower than systemic circuit. That is all correct. So we can say is this, the blood pressure is lower than the systemic circuits. But when you look at the image on the right, the top right image, you can see it says high pressure and low pressure. What this means is this, is that the blood pressure in the first half of the pulmonary circuit is higher than the second half of the pulmonary circuit. So what I want you to know is this, is like I said a while back, was that the heart is a pump. It takes a lot of force. It has to generate a lot of force to push the volume out of the heart and into the circuits. So what that means is anytime blood leaves the heart, it leaves the heart with high pressure, and the pressure itself produced by the heart is used to push the volume, to drive the volume across the circuit. So by the time the blood volume comes back into the heart, the pressure gradually dies out. So which means that the second half of the pulmonary circuit, the pressure gradually decreases. So as you can see from the image that we have, in both images, but let's go back to the top images, is that the pressure in the first half of the pulmonary circuit is higher and the pressure in the second half of the pulmonary circuit. All right, very good. So we are done with the discussion of the pulmonary circuit. Let's go into the discussion of systemic circuit. Okay. So what does it begin? What does it end? That's the question. Okay. So what does it begin? What does it end? So in terms of the systemic circuit, we can say is that the moment blood leaves the left ventricle, it goes into what's known as your systemic circuit. But let's talk into more details on this. Let's go into more details on this. So we want to begin with the left ventricle. It goes into, so this is going to distinguish the systemic circuit. We can say systemic arterial system, systemic capillary beds, and systemic venous system before it goes back into the right atrium. So and the reason why I use a very generic term in terms of systemic is because when you think of systemic, it could be going to any organ. And when I say any organ, here's an example of what I mean when I say any organs is that it could be the heart, it could be the spleen, it could be anything, right? And we know the main artery that leads the heart or that connects to the heart is the aorta. And the aorta by definition by definition is the largest artery in the body. And the aorta will give rise to many branches, and these branches will branch out again, and these little branches will feed into the organs, respective organs. So in general, every organ has one main artery and vein, with a few exceptions. What we can say is this, so what we can say is this, to summarize this, every organ has a respective artery that carries nutrients into the organ, and it has vein to drain out waste from the organ. So in essence, we can talk about how the arteries branch out into smaller arteries and how the veins converge and fuse together and merge together to form larger veins. We will come back to that, all this in a moment, okay? But for now, let me just basically, let me just type this in for you and before I move on, okay? Good, fantastic. And I'm gonna move this back up. So, okay, very good. Okay, now, as you can see from the systemic circuit, it's lengthy, so it's longer, right? So we can just actually add the word longer. Okay. Now, compared to the pulmonary circuit. Now, as you can see from the gas content, okay, now let's talk about the gas content. You can actually look at the images, the two images on the right side. Now, in the circuit itself, you can see that it contains the systemic circuit has two colors. Okay. The first initial half of the circuit is red. The last half of the systemic circuit is blue. So what that means is it's the same concept as the pulmonary circuit, except we can say oxygenated blood in the first half of the circuit and deoxygenated blood in the latter half of the circuit. Okay, very good. So you can see from this is that we have in the first half of the circuit, you can see it has oxy blood in the first half. In the second half of the circuit, you can see it has deoxy blood in the second half of the circuit. In terms of resistance, okay, in terms of resistance, as I mentioned before, the resistance correlates with the length of the circuit. Okay? And what that means is this, is that since there's a longer distance in the systemic circuit, the resistance is higher in the systemic circuit when compared to when compared to the pulmonary circuit. Now, once again, is the blood pressure in the systemic circuit tends to be higher than the pulmonary circuit. So it's higher than pulmonary circuits. So if you look at the image that the top or the bottom image, the top image actually shows you the pressure changes within the circuit. So like I said a while back, I said that every time blood leaves the heart, it leaves the heart with high pressure. And the reason why is this, the pressure is produced by the heart when it contracts. So when the heart contracts, it ejects the volume out of the heart with high pressure. So to ensure that the blood volume travels throughout the respective circuits, and as the blood returns back into the heart during relaxation of the heart, the pressure gradually dies out as the blood travels back into the heart. So we can say this, in the first half of the systemic circuit, the blood pressure is higher than the second half. So we can type in is the blood pressure in the first half of the systemic circuit is higher than the second half of the systemic circuit. Okay, does that make sense? So let's talk about the pulmonary circuit and systemic circuit. Once again, let's summarize this. Okay, so as you can see, pulmonary circuit is relatively short. It goes from the heart to the lungs and from the lungs back to the heart. In your systemic circuit, it goes farther out because the blood has to go all the way to the head region, and it has to go all the way down to the feet region, which means that the distance from the heart into the head is longer, and also the distance from the heart to the feet to the toes is also long as well. So in total of distance wise, the systemic circuit is a lot longer than the distance in the pulmonary circuit. Any question on this? Good, let's move on. So write down the question and we will discuss the answers, the question and the answers in the Q&A session. Now let's examine the wall of the blood vessels. When you look at a blood vessel, you see is that there are distinctive differences between the arteries, the capillaries, and the veins. Okay. So first and foremost, let's look at the wall. Only look at the wall of the blood vessels. Typically, the blood vessels has 3 layers. So typically this is how the design of the wall of the blood vessels. So the word tunics means layers. So let's begin with the word tunica interna. Okay. Now, based on the name, you can say is that this is the innermost layer of the wall of the blood vessel. In addition to this, the tunica interna, function-wise, what it does is since it's the innermost layer of the wall of the blood vessel, what it does is that it provides lining to the, or we can say inner lining of the lumen of the blood vessels. So you can see the inner lining of the blood vessel is formed by tunica interna. Now, as you guys look at the name on the right side, the right image, it doesn't say tunica interna, but rather tunica intima, so which means that tunica interna is also known as tunica intima. Now we're done of that. Let's move on to the next one. Is this tunica media? Okay, in the name itself, tunica media just means what? Tunica media is the middle layer of the wall of the blood vessels. So this would be the middle layer of the wall of the blood vessel. Okay. Now this middle layer contains smooth muscles. So we know for a fact is that these smooth muscles is controlled by the autonomic nervous system. So what that means is that this smooth muscle is involuntary. You have no control of this smooth muscles. So it's controlled by the autonomic nervous system. So this layer contains the smooth muscle. So smooth muscle of the tunica media controls the size of the lumen. So we use the word vasoconstriction or vasodilation. So vasoconstriction, vaso means blood vessels. Vasoconstriction or vasodilation just means vasoconstriction means it constricts, which means the lumen is going to decrease. Vasodilation is when it is increased. So if you look at the image on the left side, you can see when you have vasoconstriction, the lumen is decreased. So if you look at the left side, when you have vasoconstriction, the lumen is decreased. When you have vasodilation, the lumen is increased. Now, moving on to the next one is going to be what's called tunica externa. And this is also known as, aka tunica adventitia. Now, this is the outermost layer of the, so this is the outermost layer of the wall of the blood vessel. And the color doesn't really mean anything. It's just because I want to contrast between the words and the color of the images. Okay? Now, so what we can say is this. So it's basically it's the outermost layer of the wall of the blood vessels. Okay, so we are good for that. Let's ask a question on this. Okay, so let's ask a question on this. Okay, so let's go move on to the next one. And I'm going to show you basically is that, so let's, oh, forgot to, before we go on, I want to basically mention something really quick is this. If you look at the blood vessels, the three blood vessels that we have, the three types of blood vessels. So three types of blood vessels. We have 1, the arteries, 2, the capillaries, and 3, the veins. Okay? So we can say typically the arteries have 3 tunics within the wall. Okay? The arteries have 3 tunics in the wall of blood vessels. All right. And with exceptions, okay, so what we can say is this, is that not all arteries have 3 layers in the wall of the blood vessel. So we can say in the blood vessels, with exceptions. And the exception would be what's known as arterial, okay, only has 2 layers in the wall of the blood vessels of that respective blood vessel. So arterial is a type of arteries that we would talk about in more details in the next slide. So now the capillaries only has 1 layer of layer in the wall of the blood vessel. Now the veins resembles that of the arteries. So typically veins have 3 layers in the wall of the vein. With exceptions, and the exception is going to be the venule only has 2 layers in the wall of the venule. We will come back to this in a moment. It might sound confusing now. Bear with me on this, but it will make more sense in a moment. Let me just briefly go over the image that you see at the bottom of this. You can see that I'm going to zoom in, and you can see pretty much basically the 3 layers of this. You can see in the artery, we have the 3 layers as 1. Let me just try to move this down to here. 1, 2, and 3. Okay? 1, 2, 3. In the capillary, you can see there's only 1. In the vein, you can see 3 layers as well. 1, that doesn't help because it has the same color. I'll put black as well. Okay. 1, 2, and 3. All right. So I'll change the color to this as well to make it black, because black is more distinctive in the sense of this is because, yeah. And I'll do the same thing with this as well. For the capillary, there's just 1. I'll use a different color. Okay, good. All right, we'll come back to the next image. In the next slide, we will go into more details on this. All right, so let's examine the arteries and the veins. And as you can see, typically, if you look at the arteries and the veins, there are 3 types of arteries and there are 3 types of veins. So what we can do is we can summarize this and say there are 3 types of arteries, and they are going to be known as elastic, muscular, and arterioles. Okay. The elastic is by far the largest, so this will be number 1. Okay, we can describe this as the largest in size. And we can also say this is that it's proximal to the heart compared to the other type of arteries. So I'm going to make a distinction. So this is a comparison between within the arteries itself, not comparison between the veins or arteries, but this is a comparison within the arteries itself. So it's the largest and proximal to the heart. And in terms of it contains the highest blood pressure among the three types of arteries, among the arteries. So elastic artery is very, very elastic. It contains the highest blood pressure among the arteries. And because it's very proximal to the heart, it receives the highest pressure that the heart generates as it pushes the volume out of the heart. And because it's very elastic, it is able to, so because of its elasticity feature, this type of artery, elastic artery, can bear the blood pressure without rupturing. So what that means is this: as blood goes into the elastic artery, the elastic artery can expand out and recoil because of its elasticity. And so as you can see from this, the elastic artery has all three layers. You have what's called tunica adventitia. That's the first layer that we have on the outside. 1, 2. Well, let's go backward on this. Okay, we can say 3, 2, 1. We say 3, 2, 1. One's on the outside. So 3, 2, 1. Or we can go 1, 2, 3 in this, which makes it easier. Doesn't matter which way, but it's still the same thing. So we can say 1, 2, 3. All right. So we have tunica adventitia, tunica media for 2, and tunica intima for 3. All right. So the intima is the innermost. And the adventitia is the outermost layer. Okay. Very good. Now moving on to the next type of artery, we have muscular artery. And muscular artery, basically the way it's named is based on, so let me give you an example, and I forgot to give you examples of elastic artery. Example of elastic artery is going to be examples of this. So example of elastic artery is, so let's go with this. Example of elastic artery. Example, aorta, common carotid, common iliac artery, brachiocephalic trunk. So these are just a few names that shows you that these are examples of elastic artery. If you look at the name of these arteries, you can tell that they are larger in size compared to the average arteries. So for that reason, they are by far the largest type of artery among the three types. The muscular artery is not the largest, nor the smallest, it's in between. So what we can say is it's typically named in accordance to the location. Okay. So typically what we can say is this, is that muscular artery are the one that are named based on location. For example, brachial artery. For example, brachial artery. Brachial artery is an example of a muscular artery, and the reason why it's called brachial artery is because it's in the brachium. Okay, so which means the muscular artery is named based on location where they are found at. And like I said, the muscular artery is not as big as elastic, but not as small as the arterial. So it has all three layers. We can say it has what's known as adventitia. We can put this as 1. It has what's known as muscular 2, and it has what's known as the intima 3. Now I want you to know the endothelium is a part of the tunica intima. So when you look at the word um, endothelium, it is also a part of the tunica intima. Now the third type, and by far the smallest type of artery, is the arterioles. The arterioles by far is the smallest and the smallest size artery, and it's the most distal from the heart compared to other arteries. Now keep in mind this is a discussion among the arteries, not with the veins. We're comparing within the 3 types of arteries. So the arterial is the smallest of the 3 types of arteries. It's most distal from the heart, and it only has 2. So unlike other arteries, other types of arteries, the arterial only has 2 layers, and they are going to be tunica, media, and interna. Okay. But no tunica externa. What I also and did not tell you guys is that between the arteries and the veins, if you look at the thickness of the 3 layers in the arteries and the thickness in the 3 layers of the veins, the tunica, the arteries, the tunica media is thickest among the 3 layers in the wall of the arteries. So the tunica media is the thickest among the 3 layers in the wall of the arteries, which really makes sense because, as you can see, the pressure in the artery tends to be higher, and for that reason, the pressure, the muscle in the artery must be thicker when compared to the vein. And what I also need for you to know is that because the tunica media is very thick in the arteries, the arteries do not collapse in the absence of in the absence of blood. So what we can say is that the shape we can say is this: the artery does not collapse in the absence of blood. So when there's no blood in the artery, it does not collapse, unlike the vein. The vein collapses when there's no blood in the vein. And the reason why that is so is because the vein the wall of the vein is very thin compared to the wall of the artery. So we finished the arteries, and it's a very discussion. And by the way, the arterial has no name because there are more of them. Okay, so we can also say this is that there are more. So in general, we can say this: there are more arterial than elastic and muscular artery. And the reason why is this, and the way it works is this: is that the elastic. So we can summarize also one last comment to be made is that typically arteries, larger artery branch out to form smaller arteries and so on. Okay, so what that means is this: is that the pattern of arrangement for the arteries is divergent, which means they are branching out. So we have larger arteries branch out into smaller arteries, and smaller arteries branch out into smaller and smaller arteries. So we can see the largest one is elastic. The elastic artery branch out into the muscular arteries, and the muscular arteries branch out into the arterioles. So unlike the other arteries, the arterial does not have name, and the reason why is because there are so many of them, and you can't really possibly name all of them. So the arterial has no name because there are so many of them. Now let's go into the capillaries, and in the capillaries you can see basically it's this different type of capillaries. So let's talk about the three different types of capillaries and why there are different types of capillaries. So typically we can say this is that the capillaries have one layer in their wall. Okay, the wall. Why don't we say in the wall of this blood vessel? So what they have is they only have what's called the tunica interna. That's it. Now the next question we want to ask is this: is that let's examine the wall of the capillary and ask the questions. Is it one? Is there any gaps? Or there's no gaps. Okay. So what that means is this: is that first question we want to ask is this: if there's no gap, then the blood vessel, the capillary is called continuous capillary. If there are gaps, then the blood vessel has different names. Gaps present in the wall. Then this would be known as, it could be known as one, that'd be called fenestrated capillaries, which means there's small gaps in the wall of the capillaries, or sinusoid, which are capillaries with large gaps in the wall of the capillaries. So you can see from this, from the image of the capillaries, we can say the continuous one. In the continuous one, there's no gap in between. And whereas in the fenestrated and the sinusoid, there are gaps within the wall of the capillary. Let's go into the veins. Now, once again, there are three types of veins that we can discuss about. So there are three types of veins. Three types of veins. Okay. So they are venular. So now instead of going from largest to smallest, I'm going to go from smallest to largest. And I'll tell you why in a moment. Venule is the smallest medium-sized vein. I'm curious, how big is that? Well, it's not the largest nor the smallest. It's in between and large vein, okay, or large size vein, which is by far the largest of the three veins. Okay. Now, what we can say is this, is that in the vein, the tunica externa is the thickest among the three layers in the wall of the vein. Okay. With a few exceptions, well, not with exceptions, but we can say this, not all veins have three layers, right? Okay, good. Now, what we can also say is since the wall of the vein is thinner than the arteries, than the wall of the arteries, therefore, veins collapse in the absence of blood. So if there's no blood in the veins would collapse. So when you look at the wall of the veins under the microscope, you can see that the vein does collapse because of its size. Now the next one's going to be, we can see, so let's examine this in a moment, okay, right now. Let's begin. I'm going to go from the smallest to the largest. Okay, so the venule by far is the smallest vein, and it's the most distal from the heart. And when I say the vein, the most distal, compare among the veins themselves. And unlike other veins, the venule only has two layers, and they are going to be known as tunica externa and tunica interna. No tunica media. All right. You can see adventitia means what? Is a part of tunica externa. Endothelium is a part of the tunica interna. Now, a comment I can make in this, in terms of the veins, is that we can say, typically, in this context, we can say, typically veins. So, typically, smaller veins merge to form larger veins. And the pattern of arrangement for the vein, pattern of arrangement for the veins is convergent. That means merging together to form larger veins. So smaller veins merge together to form larger veins. And for that reason, I want to begin with the venule and go into the medium-sized vein and going towards the large vein. Now, let's recap on both of the pattern of arrangement for the arteries in the vein. The pattern of arrangement for the arteries is divergent, which means is that the largest artery connects with the heart, and this artery branches out into smaller arteries as they carry oxy blood into the organs, while the veins converge, which means that the veins carry deoxy blood out of the organs, and these veins converge from small into bigger veins as they drain the deoxy blood away from the organs and back into the heart. Okay. So once again, you can see the basic arrangement of the arteries is divergent. The basic arrangement of the veins is convergent. Okay? Now let's go into the medium-sized vein. Medium-sized vein is not the largest nor the smallest, it's just in between. You can see in this case is that there are 3 layers. We can say 1, we can say 2, and 3. Okay, so there are 3 layers in the medium-sized vein. And it has the same name as this. So typically medium-sized vein has the same name as so medium-sized vein is typically named, named in accordance to location. Example, brachial vein. Where can you find that? Very good. Brachial artery. I'm sorry. Brachial vein could be found in the brachium. I got carried away, by the way. So the brachial vein could be found in the brachium. And what we can also say is this, and I'll come back to the last comment we made in a moment. Now, the same goes for the large size vein. So what we can say for the large size vein is it is going to be by far the largest in size, is proximal to the heart, and this has by far is going to be the largest in size, so which means it receives all of the deoxy blood from other veins, smaller veins, before it returns the deoxy blood back into the heart. So in general, what we can say is that typically veins carry deoxy blood typically, and arteries carry oxy blood typically. There are some exceptions, and we will talk about the exception in a moment. For now, we know that veins carry deoxy blood typically. Arteries carry oxy blood typically. Very good. So let's begin. Let's summarize things really quick. Is that there are 3 different types of arteries and 3 different types of veins. Okay? And before I move on, I'm going to basically label it 1, 2, 3. Okay, so the 3 layers within the large vein. Okay. Now, what can we talk about this in this moment right now? Is this we can say. What else can I add to this? I believe that's pretty much done. I mean, it's a very extensive comparison between the arteries and the veins. And so we can just move on. If you have any question, basically make sure you write down the question, and then I will address the question in a moment, in the Q&A session. Oh, one last comment I want to make before we move on is this. One last comment. If you notice that based in this image right here, the size, the artery and the vein, they travel together, which means they are found within the same location. And this is, I know this sounds confusing, but this makes more sense. Is that the comment I want to make is going to be, we can say, the comment I want to make is so bear with me on this. I'm gonna make this comment right now, and I want to find a space where I can write the comment within. Okay. So what we can say, this comment is a very good comment to be made. We can say artery and vein of similar size travel together. That means they are found in the same location, but carry blood in different direction in reference to the heart. Okay. What that means is this: artery and vein of similar size travel together. So the artery and the vein, so for example, muscular artery and medium-sized vein, they are found in the same location, but the artery carries blood away from the heart, while the vein carries blood back into the heart. So what we can say is this: artery and the vein of the same size travel together, but they carry blood in different direction. In reference to the heart, they carry blood in different directions in reference to the heart. Very good. So this is a very extensive, it's a comment that we can make that can depict the commonality that despite the fact that they carry different type of blood, we can say that they resemble each other in various aspects. Uh, okay, good. Let's move on to the next slide. Veins. So we know, I mentioned a while back and I said veins have lower blood pressure than arteries. That's obvious. Okay, so in general, we can say this. We can say, if you remember what the comment I made a while back, I said arteries carry blood away from the heart. And, with higher pressure. So, or we can say this, arteries contain higher pressure to drive blood flow away from heart during cardiac systole. That makes sense, right? Which means it says that the arteries contain higher blood pressure to drive blood flow away from the heart during cardiac systole, which means contraction. Veins contain lower pressure to return blood flow back into the heart during cardiac diastole, which means relaxation. So the arteries contain higher pressure to drive the blood flow away from the heart during cardiac systole, which means contraction. Veins contain lower pressure to return blood flow back into the heart during cardiac diastole, which means relaxation. So, when the pressure drops, how is it? So the question we want to ask is this, the question we want to ask is going to be, what mechanisms are used in the venous system to overcome the low venous pressure in order to maintain the blood flow without interruption? And the answer is, the answer is, there are different factors or different mechanisms involved, and we are going to discuss on this. Okay, so now this is when we want to discuss on the answer to this question. So going back to what I was telling you guys a while back, I said that veins have lower pressure than the arteries. That is understood. Okay, so that is understood. And we can also say in this case is that we can say arteries have higher pressure than the veins. That's obvious. So veins have lower pressure. That means arteries must have higher pressure. That's obvious. So the venous system relies on various mechanisms to maintain the venous blood flow despite of the low venous blood pressure. So these are the mechanisms being used by the veins to overcome the low venous blood pressure in order to maintain the blood flow without interruption. Blood should not stop. Blood flow should not stop. It has to be maintained in a very consistent manner. Consistent, not constant, consistent manner. So the blood flow must occur, and when the blood pressure drops for any reason, the body will compensate to increase um, the pressure needed to maintain the blood flow. And for that reason, we refer to it as homeostasis. So when you use the word, so when you think of homeostasis, everything must be consistent, not constant, because it's a very dynamic state. So everything must be consistent. So when you think of the mechanisms involved, there are three mechanisms involved, and the first one is called the tunica media of the veins. What exactly is the tunica media of the veins? We have talked about this, prior. The tunica media of the veins contains smooth muscles. Now, even though the tunica media of the veins is not as thick as the artery, but the smooth muscle itself thus contributes to the pressure, to the venous pressure. But because it's thinner than the arteries, its contribution to the venous pressure is not as extensive. And for that reason, the venous pressure is not as strong as the arterial pressure. But regardless, the tunica media does contribute to the venous pressure. The next one is so you can see from this image right here, right here, the tunica media does contribute to the constriction of the veins. So we can say is this venous constriction So venodilation or venoconstriction means that the smooth muscle of the tunica media either relaxes to produce venodilation or contract. The smooth muscle contracts and produces venoconstriction. The valve in the veins, as you know, the valve in the veins resemble to the function of the valves in the heart. So when you look at a valve in the veins, what we can say would be the valve, like any other valve, its main function is function of the valve is to prevent the backflow of blood in order to maintain unidirectional blood flow. So you want to keep blood flow in one direction, so which means blood should not go backward. So that is the uniqueness compared to the arteries, the veins have valves. Now, the third mechanism that is used by the vein to maintain the blood flow within the vein is the muscles around the veins. So these are called surrounding skeletal muscles. So what's very unique, what's not unique is that when the surrounding muscle contracts, their bulkiness compress on the vein to provide additional pressure, so to facilitate the blood flow in the venous system. When you look at these two images that we have here, the left and the right side, So here's what we have is this muscle is relaxing. On the right side, you can see the muscle contracting. When the muscle contracts, they become bulky, and the bulkiness of the muscle will produce a compression on the vein, which provides more pressure on the vein to increase or to maintain the blood flow in the venous system. So they always recommend is that you never want to be static, which means you should be moving around. As you move around, you increase in your blood circulation, which means that the muscle contraction does help the veins to maintain the blood flow. And so one of the things they say is this, is that they said when you move around, you decrease the chance of having varicose veins. And so this is one way of, and we'll talk about varicose veins in a moment. All right, any question on this before I move on? So let's go back. Let's just basically this. We can say, summarize this. We can say the blood pressure in the artery is higher than the blood pressure in the vein. For that reason, the blood flow in the vein would not be maintained unless we use various mechanisms to overcome the low venous blood pressure. And the whole compensation is to maintain and the purpose behind the compensation is to maintain the venous blood flow. You want to keep the blood flow to be consistent. And the three mechanisms are used are tunica media of the veins. That's a smooth muscle in the vein. Even though the smooth muscle is very thin in the vein, it does make contribution to the venous pressure. The valve in the veins, like any valve, prevent backflow. So what it does is that it helps to maintain unidirectional flow in the vein. And the last one, which is more important, is the skeletal muscles around the veins, on the outside of the veins. So when these muscles contract during movement per se, what happens is that these muscles become bulkier when they contract, and the bulkiness of the muscle compress on the veins from the outside, which add the pressure to the venous system so it can maintain the venous blood flow. Any question? Write down your question and we will discuss the questions in the Q&A session. Okay, good. Moving on to the next slide. Varicose veins. Okay, so varicose vein is a condition in which what causes varicose veins, or what exactly are varicose veins is the veins becomes dilated and tortuous. It's larger in size and it's very winding. Okay. And the reason why it's dilated and tortuous is because due to the damage valves of the veins. So let's begin with the images on the right and the left side. Okay. And what that means is that since the veins are damaged, that means blood collected or pooling the blood, causing the blood to leak backward and pool or collect and be collected within the veins. So the veins become like it bulges out. So let's look at the image on the right side. You can see these veins are larger. So on the right thigh and the right leg, you can see that the veins are these veins pop out. They are large in size and they're very winding, tortuous. Now moving on to the left side. In the left image we have is this. We have two different types of veins. The top would be normal vein in which the valve is working. On the bottom image, we have what's known as the valve is damaged. So as a result, the blood leaks backward. And for that reason, the blood collects within this segment of the vein. And for that reason, it becomes bulkier or it bulges out. And one of the way that to decrease this is by having more movement. So if you move around, what would happen is that the um, the pressure produced by the muscles or the muscle contraction causes the muscle to become bulkier, and the bulkiness of the muscles compress on the veins, which provides additional pressure on the veins to move the blood flow in a consistent manner. Now, let's make a comparison among the blood vessels. Let's make a comparison among the blood vessels. And we can basically let's compare. What is the function of the arterial system by definition? We can say the arterial system transports blood away from the heart. The structural arrangement of the arterial system is divergent. What that means is this is large blood vessel branches out to form smaller blood vessels. Arteries typically have 3 layers. So typically, arteries have 3 layers except the arterial, which only has 2 layers, and there's no tunica externa. We also know is that the tunica, so number 1 is, we know for a fact in this case the layers of the arteries, we can say typically arteries have 3 layers except the arterial. And we know of the 3 layers, the tunica media is by far the thickest of the 3 layers. The gas content in the arterial system. So typically, once again, typically, arteries contain oxygenated blood, with exception pulmonary trunk, pulmonary arteries, and umbilical arteries. All of them have the oxy blood. So typically, arteries contain oxy blood with exceptions. The pulmonary trunk, the pulmonary arteries, and umbilical arteries all have the oxy blood. The pressure in the arterial system is higher than the pressure in the veins. The lumen size of the arterial system is smaller than the lumen of the venous system. Okay. But this is a very good comparison of among the arterial system itself. So we can generally say the arterial system transports blood away from the heart. It has a very divergent arrangement. And when I say use the word divergent arrangement, we can say that the blood vessel branches out to form smaller blood vessels. And typically, the arterial system has 3 layers, with exceptions of the arterial. And the thickest layer of the 3 is tunica media. The gas content in the arterial system is typically oxygenated, with exceptions: pulmonary trunk, pulmonary arteries, and umbilical arteries. The blood pressure in the arterial system is higher than the blood pressure in the venous system, and the lumen size of the arterial system is smaller than the lumen size of the venous system. Very good. Let's go into the capillary beds. So we know the capillary is a site of exchange of nutrients and waste, period. And if you look at the image on the bottom image, you can see that the arrangement of the capillary is parallel. So they are parallel to each other. So they're not divergent nor convergent. So it's not divergent nor convergent. And we know it only has 1 layer. And the gas content is going to be a combination of both. So we can say this gas content in this case is going to be both oxygenated and deoxygenated. So prior to the exchange, and so it's both. It's a mixture of both. It's a mixture of both. It's a mixture of oxygenated and deoxygenated. And the pressure itself is individually pressure is weakest, but collectively the combined blood pressure is higher. And the lumen size is the same thing. So we can say this, the lumen size is individually the capillary has the smallest lumen size. All right, let's move on to the veins. In the venous system, its main function is transports blood back into the heart. And the arrangement of the venous system is convergent arrangement. What that means is that arrangement. What that means is that the veins merging together. So what we can say is smaller veins. So what we can say is smaller veins merge together to form larger veins. Now the venous system has typically, once again, veins have 3 layers, except the venule, which only has 2 layers, and which has 2 layers, no tunica media. And by far, the tunica externa is the thickest of the three layers in the vein. Very good. And the gas content we can say is that we can say typically veins have contained deoxy blood with exceptions. And they are going to be what's known as pulmonary veins and umbilical vein, and which all have oxy blood. When I say all, these are the exceptions. So the exceptions all exceptions, in this case, all exceptions have deoxy. So all exceptions. So all exceptions. So let me add this right here. So all exceptions in the vein, all exceptions in the vein have oxy blood. The pressure in the vein is lower than the blood pressure in the arterial system. And the lumen size in this case is the lumen size of the vein is larger than the lumen of the arterial system. Now, two last comment I want to make is this. Two last comment I want to make is the arteries, the arterial system, I should say, arterial system has higher blood pressure. And for that reason, therefore, they are referred to as pressure reservoir. While the veins, the venous system, has larger lumen size, and for that reason, they are referred to as volume reservoir. What that means is that veins can hold more volume, blood volume, than arteries. All right, so any question this, write down your question and we will come back to the question in the Q&A session. All right, let's go into what's called hemodynamics. Hemodynamics, so dynamics means changing, right? Changes occurring. So hemodynamics is the study of the forces involved in blood circulation. So first thing is this, blood flow. Blood flow to different parts of the body changes depending on demand. So there's a demand and supply factor involved. Okay, so what that means is this, is that we can say when you think about demand and supply, like in economics, the more demand there is, the more supply there should be, right? And so it's the same thing in this case is that demand represent demand of oxygen by the by the organs, which would cause the supply versus the supply of blood flow to the organ to meet the demand of the organ. Okay, so demand versus supply, that's the question that you always want to ask. So example of this would be when you exercise, there's an increase in oxygen demand by the muscles that you use to exercise. And as a result, there's an increased blood flow to the muscles. The same thing goes for eating. After you eat, the nutrients are absorbed, which means there's a demand for blood flow to the GI tract for absorption. So what that means is this, is that when you absorb nutrients, the nutrients that you extract from the food that you eat will be absorbed across the wall of the small intestine to be absorbed into the bloodstream. So when you think of absorption, so in a nutshell, we can say in absorption, you're moving. So in absorption, we have movement of, so in absorption, you have movement of nutrients are uptake from the lumen of the small intestine across the nutrient. So let's repeat what I just said. In absorption, you have nutrients are uptake from the lumen of the small intestine across the or into the bloodstream. When you absorb, you uptake the nutrients and move it from the lumen of the small intestine into the bloodstream. So, so what we can say is this, is that hemodynamics is referred to as the forces involved to maintain blood circulation. So let's rewrite this. We can say is referred to as the force. So in hemodynamics, we examine what's known as the force needed to maintain blood circulation. So the changes of blood flow depends on the demand of the nutrients or the oxygen by the organ, and the demand goes up or down based on the state of the body at that moment. So when you're exercising, there's more demand of oxygen in the muscles used to exercise, and for that reason, the blood flow rediverts to the muscles. When you eat, the blood flow will redivert to the GI tract or digestive tract for the uptake of nutrients into the bloodstream. And for that reason, there's less blood flow to the muscles. And for that reason, you feel very weak after you eat. Because why? There's more blood flow to the GI tract and less to the muscles. And for that reason, you feel tired after you eat. Ooh, okay. So the next slide. Oh, let's talk about this. Okay, so what we can also say is this. Let's I'm gonna pause for a moment. So let's say an equation I want you to know is this. So the equation I want you to know is flow is equal to, so the blood flow is equal to the pressure over resistance. All right. So one thing we want to ask is this. We can say when the resistance, if there's an increase in resistance, so the blood flow is always consistent, or it changes based on the demand of the organs, but the pressure basically and resistance. Now the question we want to ask is this, is that what dictates the resistance? Okay, so these are the factors that affect the resistance. The factors that affect the resistance are going to be the radius of the blood vessel. So in the case of dilation and constriction, the larger the radius, the less the resistance within that blood vessels. The factors affecting resistance. So the first factor is the radius of the blood vessel. The next one would be what's known as viscosity of the blood. And the third would be what's known as the length of the blood vessel. All right, let's begin with the first one. Okay. When you look at the radius, oh, by the way, before I do anything, I'm going to ask the question I'm going to ask the question as such as this. When you think of resistance, what does resistance mean to you? Resistance means the force that opposes movement. Okay? And it's the force that opposes movement. And what it means is this, is that the blood pressure must be high enough to overcome the resistance in the circuits in order to maintain the blood flow. So all this was mentioned in the previous lecture. So why don't we say this? Okay, blood pressure, the resistance is the force that opposes movement. Therefore, the blood pressure produced by the heart must be high enough to overcome the resistance in order to maintain a consistent blood flow. So what we can say in this case is going to be, in this case, there are three factors that affect the resistance. First factor, radius of blood vessel, which means the lumen size. Larger lumen has lower resistance, and smaller lumen has higher resistance. So when you have vasoconstriction raises the blood pressure. Vasodilation decreases the blood pressure. So when you constrict the blood vessel, the resistance would increase, and therefore the pressure must increase to overcome the high resistance. And vice versa, when you dilate the lumen of the blood vessel, therefore the resistance would decrease, and thus the pressure would decrease as the resistance decreases. Number two, viscosity of the blood means how thick, the thickness of the blood. Okay. The thickness of the blood. The thicker the blood is, or the more viscous the blood is, more viscosity requires more pressure, more blood pressure, higher blood pressure, I should say, higher blood pressure to drive this viscous blood volume across the circuit. So when you think of swimming in a pool, swimming pool, when you swim in water, there isn't that much resistance as opposed to swimming in a pool of jello. Imagine swimming in a pool of jello. How fast can you move? Not very fast, because the jello is very, very thick, and that will provide more resistance. And so, which means the more viscous the blood is, the more resistance it has, which causes the blood pressure to rise to overcome the high resistance produced by the high viscosity of the blood. Number three, the third factor is the length of the blood vessel. Now, we know for a fact is this, the longer the blood vessel is, the longer the blood vessel, the more pressure needed to drive across across the length of this blood vessel. So what we can say is this, longer blood vessel require more blood pressure to drive the blood volume across the longer distance. A lot of people ask, a lot of you guys are probably asking is that how can you increase the blood vessels? Aren't blood vessels constant in length? And the answer is no. If you gain weight, the adipose tissue that you have requires nutrients, and for that reason, when you gain weight, the blood vessels are being created to nourish. So the small branches of blood vessels are produced to nourish the excess or the extra adipose tissues. And for that reason, when you gain more weight, the resistance would increase due to the length of the blood vessel being increased. And for that reason, the blood pressure tend to increase to overcome the higher resistance when you gain the weight. So when you lose the weight, on the other hand, you have less adipose tissue, which means that the branches of the blood vessels that help to nourish these adipose tissue would decrease, and the overall length of the blood vessel would decrease, which mean that the blood pressure would decrease. Okay, so what we can say is this: the correlation. Let's summarize this. The correlation of this. We can say, in this case, we can say an increase in the length of blood vessel, as in the case of gaining weight gain would cause an increase in, or would result in an increase in resistance. Therefore, to compensate the blood pressure must increase to maintain must increase to overcome the high resistance, so to maintain the blood flow. And the same goes for the viscosity of the blood as well, same thing. An increase in blood viscosity would result in an increase in resistance. To compensate, the blood pressure must increase to overcome the high resistance, so to maintain blood flow. And the third factor is the radius of the blood vessel. An increase in the radius of the blood vessel, which means larger lumen, would result in a decrease in resistance, to compensate the blood pressure will drop to to maintain the blood flow. Okay, so keep in mind is that when there's an increase in the length of the blood vessel, the resistance would increase as well, and to compensate, the blood pressure must increase. If there's an increase in blood viscosity, the resistance will also increase, and to compensate, the blood pressure must increase as well. If there's an increase in the radius of the blood vessel, which causes the lumen of the blood vessel to become larger, and as a result, the resistance would decrease, so to compensate, the blood pressure would drop. So once again, it is an increase in the size of the lumen of the blood vessel would cause the resistance to decrease. So to compensate, the blood pressure would drop. Last slide is the blood pressure. What is being measured when you look at the blood pressure is this. Okay. So when they measure the blood pressure, they give you two values: systolic pressure versus diastolic pressure. So when systolic pressure is being defined as the blood pressure being measured during cardiac systole. What that means is that the pressure is being measured when the heart contracts to eject blood into the two circuits. Diastolic pressure represents diastolic pressure represents the blood pressure being measured during cardiac diastole, which is the pressure being measured. The pressure is being measured when the heart relaxes as blood returns back into the heart from the two circuits. So typically when you measure the blood pressure, you produce two values: the systolic pressure and the diastolic pressure. Systolic pressure represents the blood pressure being measured when the heart contracts, and the diastolic pressure is measured when the heart is relaxed. If you remember what I said, there are two events that happen during one heartbeat: systole and diastole. So in one heartbeat, two events occurring during one heartbeat: systole, cardiac contraction, and diastole, cardiac relaxation. All right, that's pretty much it. So we are done with the vascular system. So this is the last portion of the cardiovascular system. So if you have any question, write the questions down and we will discuss the questions during the Q&A session. All right, study hard.